now going to go through Chapter 15's homework. I will start off by saying it was a lot more challenging than Chapter 14 homework. So hopefully I'm able to help you guys and it makes a lot more sense after I go through it. And know that I am here to help you. Number 1, we're told we have a saturated solution of an unknown metal hydroxide with a measured pH of 8.67, and we want to find the value of KSP for this compound. So KSP, that's solubility product, so we can assume that this reaction then is this metal hydroxide is going to be dissociating to M2 plus 2OH minus. So the value of KSP, this MOH2 is usually solid, so that's going to be equal to the concentration of M2 plus times the concentration of hydroxide squared. The metal hydroxide is not in the solubility product expression, remember that, because it is a solid, it is a pure substance, if you will. So we're told pH, and we can use that to find our POH, and use POH to find OH. So our POH is equal to 14 minus 8.67, and so that is 5.33. So then that is POH, so then our hydroxide concentration is equal to 10 to the negative POH, so 10 to the negative 5.33, which is 4.68 times 10. Whoa. Don't look away and try to write at the same time. There we go. 4.68 times 10 to the negative 6 molar. Now, if we were to very quickly look at the reaction and think ice table, there's not going to be any here, but we will have some gain of X and gain of 2X for hydroxide. So that tells us that the concentration of our metal is equal to 1/2 the concentration of hydroxide. There's twice as much hydroxide as metal when we are at equilibrium. So our concentration of metal is equal to 1/2 the concentration of hydroxide, which is 1/2 times 4.68 times 10 to the negative 6th. So that is equal to 2.34 times 10 to the negative 6th molar. So now we can calculate KSP. So it's equal to 2.34 times 10 to the negative 6th times 4.68 times 10 to the negative 6th squared. Don't forget that squared. And then you get 5.10 times 10 to the negative 17th. I just want to check my math on my calculator really quick. I promise you I don't do the math that quick. I do all these problems first on paper, and then I write, and then I go through and do it again for you guys. And that's squared. Now that times 2.4. And sometimes I just go back and check my work. Yep, or actually, with rounding error, I get 5.13, but yeah, so about 5.10 times 10 to the negative 17th power for KSP. All right, number 2, we want to know how much potassium oxalate can be added to 153 milliliters of 0.1 molar, that copper complex thing, before precipitate of copper oxalate begins to form. We're given a KSP and a KF. So number 2 is a bit involved. I will tell you that straight up. My scratch paper, if you want to call it, is full of scribbles of me kind of starting over and rewriting things just to help myself out. So let's go ahead and first write one of our reactions here. So this copper ammonium complex thing, okay, it has a 2+ charge for just that ion. Okay, and so this is going to be in equilibrium with copper 2 plus and ammonia. Okay, so that ion is just because it's got this chlorine on it. That's the -2 charge, and you put that in water, it's going to dissociate into positive and negative charges, and then from there it can break apart into the copper and ammonia. So for this, we have a K equal to Cu2 plus times ammonia over our complex. And if you were to look at this, this is 1 over the Kf, because Kf, notice it's of the complex ion, and so it's the formation of that complex from copper and ammonium. So this is just the reverse reaction. So then the K of that is equal to 1 over Kf. So that is something to keep in mind. And then we can also calculate how many moles that we have of our complex. I'm just going to put CMPX for complex. So we have 0.1530 liters of it, and its concentration is 0.1 mole per 1 liter. And so this now gives us 0.0153 moles. And this is of that whole complex or just that ion. It's the same, it's a 1-to-1 ratio. Now let's also set up an ice table for this same reaction. I'm just going to do it right underneath. Now I'm starting out with 0.1 molar of my complex, okay, because it tells us straight up right there. And we're starting with 0 copper ion, 0 ammonia. Losing X, gaining X, and the ammonia is gaining 4X, okay, because it's got that 4 in front of it. 4X, X, and 0.1 minus X. Where am I? Okay, so we can go ahead and use our assumption that X is much less than 0.1, so that becomes 0. And then we can do that K is equal to our products, X times 4X to the 4th power divided by our products, which is 0.1. And so then this becomes 256 times X to the 5th power over 0.1, which is 2,560 times X to the 5th power. And this K, remember, is equal to 1 over Kf. So 1 over Kf then is 1 over 1.1 times 10 to the 12th power, and that gets us 9.09 times 10 to the negative 13th. So you divide both sides by 2560, and then you take the 1/5 root, or put everything to the 1/5 power, and you get that X is equal to 8.13 times 10 to the negative 4th molar. And this is equal to our concentration of copper 2 plus. We are not done though. Let's see, actually I'm going to add a second slide, a blank slide, to continue this problem because it's kind of long and I don't want to erase things. So let's see, new slide, resume. Okay, so now, so we know our concentration of copper 2 plus, and we have this second reaction that's happening with copper oxalate that is in equilibrium with Cu2 plus aqueous and oxalate C2O4 2 minus. And so our equation for KSP here is concentration of copper 2 plus times the concentration of oxalate. And we are solving for oxalate. We know KSP and we know copper now. So our concentration of oxalate, C2O42-, is equal to KSP divided by our concentration of Cu2+. And we're told at the beginning that KSP is 2.9 times 10 to the negative 8th divided by what we just solved for, 8.13 times 10 to the negative 4th. So our concentration of oxalate is 3.57 times 10 to the negative 5th molar. But we're not done yet. This is not what we're asked for. We want to know how much potassium oxalate. So, and if you were to look at ChemVantage, it wants your answer in milligrams. So now we have 3.57 times 10 to the negative 5th molar, which means moles of oxalate for every 1 liter of solution. And the other thing that we were told is our volume. So we are adding to this 153 milliliters. And we're assuming here this potassium oxalate is solid. Or, yeah. So we're using oxalate ion, but potassium oxalate is what we are adding. Okay, solid potassium oxalate. I mean, if you want, you can go ahead and say that you have 1 mole of potassium oxalate, C2O42-, for every 1 mole of oxalate, if that helps. Just to simplify it a little bit. And now we know our volume that we were adding this to is 0.153 liters. So we took milliliters, turned them into liters. So that goes away. Oops. And now we have moles of potassium oxalate. But we need grams. So we're going to use good old molar mass, which is 166.22 grams for every 1 mole. And then lastly, we need milligrams, so 1,000 milligrams for every 1 gram. And then you get 0.908 milligrams. So number 2, it's overall not terrible. It's just kind of figuring out where to start, which is probably the hardest part. Because there's multiple things you need to find. So if you have a problem like this on your exam, break it down into parts. Start by writing what you know. See what you can figure out. Don't just leave it blank and walk away. Try to find something. See if you can calculate anything. And you never know, it might help you out. All right. Number 3, a pipette is used to add 30 milliliters of 0.4 molar lead 2 nitrate to a 296 milliliter solution of 0.3 molar sodium fluoride. Determine the equilibrium concentration of lead 2 plus in the final solution. And we're given a KSP for the lead 2 fluoride. So let's first write an ice table to kind of see what we need to figure out. So let's look at it for this lead fluoride. So we have PbF2 in equilibrium with Pb2 plus 2F minus. Remember, fluoride, it has a -1 charge, so you have to have 2 of them to balance out the 2 plus from lead. So if we look at our ice table, lead fluoride doesn't work. We're starting with 0 lead, but we're not starting with 0 fluoride. Okay? Because we actually are adding stuff to sodium fluoride here. So we're actually going to need to figure out how much fluorine ion or fluoride that we have when this reaction starts. So we're just going to write for now F0 and adding some X, or actually not, what did I write? Oh yes, so we're adding lead nitrate. Whoops. Okay, so notice that we are adding lead nitrate here. So we're adding some X amount. However, it's reacting with the fluoride. The fluoride is reacting away, so it's actually losing negative 2X. So we're losing 2X while we're gaining some lead because we have a source of lead 2+ that we're adding to our solution. I know this is really freaking weird and complicated, and if it helps, I am not going to give you something like this on your exam. So then at equilibrium, we have X for lead and some F0 minus 2X for fluorine. So we have a couple different areas that we're making fluorine and then we are subtracting it. So the first is we're making the fluoride ion with sodium fluoride. We have this NaF that is aqueous, and this is completely dissociating into sodium plus F minus. So we're making some moles of fluorine from sodium fluoride. It's going to be equal to our moles of sodium fluoride. Okay, so that is equal to 0.2960 liters times 0.3 moles per 1 liter. So we're just going to figure out our moles here, and this is equal to 0.0888 moles of the fluoride ion from NaF. Okay, so this is how much that we're making first from this one reaction. Remember, we have two reactions happening at the same time. Okay, so then the amount of fluoride that's reacting with lead 2+, and this is before we're at equilibrium. Okay, so that's why we don't know this F0, because this is before equilibrium. So we can say moles of F reacted with the lead 2+. Okay, and that is going to be the same as twice our moles of lead. So that's going to be 2 times 0.030 liters from the solution that the lead's in times 0.4 moles per 1 liter. And that gives us 0.024 moles of fluorine that now is reacted. So now our moles of fluorine that were at or when we're about to hit equilibrium, this F0. Okay, so this is what's actually going to be acting in the equilibrium. That's equal to 0.0888 moles minus 0.024. And that gets us 0.064 moles. So then our concentration in molarity for this F0 or F0 is equal to 0.064 moles divided by our total volume, which is 0.296 plus 0.030 liters from the two solutions. Like it's a 0.064, oops, it's 0.648 moles divided by 0.326 liters, and you get 0.1988 molar. So now we have that to add in for F0 or F0. So now we can go ahead and use our KSP expression, which is going to be equal to X times our concentration of fluorine squared, which is 0.1988 minus 2X, and that is squared. And we can go ahead and assume that X is much, much less than 0.1988. Looking at that KSP, that's really small, so this can go to 0. So we get that KSP then is equal to 0.1988 squared times X. So that's 0.03952 times X. So X is equal to KSP divided by that, so that's 3.6 times 10 to the -8th divided by 0.03952. And that gets you 9.11 times 10 to the negative 7th molar. Again, just do what I do, plug in your numbers, and you'll be fine, so you get your homework points, but I am not going to give you something like this on the exam. I think figuring out like the fluorine concentration, it's not intuitive, and I don't like things like that. So I hope that eases some worries. Okay, number 4. If 396 milligrams of silver bromide is completely dissolved in 155 milliliters of 0.09 molar ammonium, what is the equilibrium concentration of silver plus in the final solution? And we're given the K formation for the silver ammonium complex. So let's first write the reaction that forms this complex. So we have some Ag plus and 2NH3. You can see that from here. And that is making this AgNH3 to +1 complex. And let's, when in doubt, ice it out. So we're starting with 0 silver and 0.09 molar for ammonium because we're told it's right there. And we also have, oh, we don't have it yet. I'm getting ahead of myself. Okay, we don't know what this concentration that we're starting with of the silver nitrate is. We do know that we're gaining some silver here, and the ammonium is going to be gaining some 2x, but it's also going to be losing, I'm just going to call this C for complex right now. Okay, so while we're gaining some ammonium, it's also still reacting, and it's actually losing some C. I'm using that for a stand-in for the complex concentration. Some 2C, since there's twice as much. So I know this seems kind of weird, and again, this is something I am not going to give you guys on your exam. Okay, so at equilibrium we have X, and then 0.09 plus 2X minus 2C, and this is C minus X. And the expression for K formation is equal to Ag and H32 over Ag plus times NH3 squared. So we can, though, find our moles of the complex using the moles of silver, because we're going to assume that all the silver gets wrapped up into the silver ammonia complex. So our moles of, just calling it C, is going to equal our moles of silver plus. And we can find that by going ahead and using some of the information given. So we're told 396.0 milligrams of AgBr. And let's first turn this into grams, 1 gram per 1,000 milligrams. And then we know that we have 1 mole of AgBr for every 187.77 grams of it using molar mass. So now grams of AgBr are gone and we have moles. And then we have 1 mole of Ag plus for every 1 mole of AgBr. And then lastly, this whole thing is being divided by our volume, which is 0.1550 liters. And so this gets us 0.01361 molar, and that's equal to C. So now we can go ahead and substitute in for C. 361, 0.01361, 0.01361. All right, so now we have pretty much everything we need, so we can solve for x. One of the first things we can do also is go ahead and assume that x is much, much less than 0.01361. So this goes away. And then we could also get rid of this 2x. That's also going to go away. So then our KF, substituting in everything, we have 0.01361 divided by our concentration of silver, which is X, times ammonia, which is 0.09 minus 2 times 0.01361, and that is squared. Okay, and so then this becomes 0.01361 over X times 0.003941. And that is equal to KF, which is 1.7 times 10 to the 7th power. So you do some algebra and you wind up getting X, which is equal to the concentration of silver, is equal to 2.03 times 10 to the negative 7th molar. Again, just put in your numbers, do what I did. I'm not going to give you something like this on the exam because that ice table part is just really freaking weird. And I'm not even quite sure where that comes from. I don't know if that is comforting or it will scare you more, but I promise I will not give you something like this on your exam. Okay, number 5, the acid ionization constant of an iron water hydrate is 3 times 10 to the negative 6th. Compute the pH of a 0.11 molar aqueous solution of iron nitrate. Okay, so let's go ahead and write down some of what we know and what we can figure out. So one of the first things is we can go ahead and say that, or we can actually write the dissociation equation somewhat for the iron nitrate. So we take iron nitrate, FeNO3, 2. Whoops. And then what's actually going to be happening, you can put equilibrium or not, honestly, but it's forming this iron water hydrate. We can just go ahead and just say that's what it's forming. It's just completely dissociating. Okay, and this has a 2 plus charge and then 2 NO3 minus. So using stoichiometry here, we can see that the concentration of the iron water hydrate is the same as the concentration of the iron nitrate. And that'll also be equal to the concentration of iron 2 plus. So just kind of writing down some things we know, and then we were told this concentration is 0.11 molar. So now taking the iron hydrate and water, and if you remember, we talked about when these metal hydrates form, they can actually be acidic or basic. And so what's happening here is this acts as an acid. So we have FeH2O6, and it is acting as a weak acid. So we have an equilibrium. And if you remember, what it forms is FeH2O5. We get rid of one of those waters and it becomes a hydroxide. And then just plus 1. And then plus H3O plus. So let's set up an ice table for this. We know water doesn't count. We're starting with 0.11 molar of the iron hydrate. And it's losing some X, so 0.11 minus X. Over on the other side, we have 0 to start of the hydroxide hydrate and about 0 acid, plus X, X, X. And so we can use our Ka expression. It's going to equal X for the hydroxide times X for hydronium over 0.11 minus X for our iron nitrate. We can go ahead and assume that X is much less than 0.11, so that goes away on the bottom. So now we get that Ka equals X squared over 0.11, and Ka is equal to 3 times 10 to the negative 6th power. So then solving for X, you get that X is equal to 5.74 times 10 to the negative 4th power, and that is our hydronium concentration. And we want the pH, so it's good that we got hydronium. So pH is equal to the negative log of your hydronium concentration. And so that is the negative log of 5.74 times 10 to the negative 4th power. So our pH then is equal to 3.24. All right, number 6, we're told to calculate the solubility of magnesium hydroxide in a buffer solution at a pH of 10.67. And we're told the solubility product of magnesium hydroxide is 1.2 times 10 to the negative 11th. So we have a buffer pH of 10.67, and we can go ahead right away go and, hey, look, I have pH. I'm going to use that to get POH. And that's 3.33. And straight away, even if I don't know if it's going to do anything for me, I'm just going to go ahead and calculate the hydroxide concentration. So I'm dealing with bases here. Let's just go ahead and do it. Because you know what? Worst case scenario, I've written something down. Always write something down. So it's 10 to the negative POH, so 10 to the negative 3.33. So our OH concentration is equal to 4.677 times 10 to the negative 4th molar. So we have written something down. And we know that KSP, well, let's say we're not quite sure on KSP. Let's first write the reaction that's happening. So MgOH2, okay, is going to become Mg2 plus 2OH minus. So then KSP is equal to our concentration of Mg2 plus times OH minus, that is squared. And so the concentration of the magnesium, which is going to be the same as our concentration, or which is going to be the same as our solubility of magnesium hydroxide, is equal then to KSP divided by OH minus squared. So that's 1.2 times 10 to the negative 11th divided by 4.677 times 10 to the negative 4th squared. And you get 5.49 times 10 to the negative 5th molar. So that is our solubility at a pH of 10.67. All right, number 7, how many milligrams of copper nitrate can be dissolved in 294 milliliters of 0.016 molar rubidium bromide before a precipitate forms? And we're given the solubility product of the copper 1 bromide of 4.2 times 10 to the negative 8th power. So this is that, oh God, what's it called? Common ion effect. There it is. Okay, so we can go ahead and first write for copper bromide to precipitate. That would be our precipitate if we're adding copper nitrate to rubidium bromide. We have Cu plus Br minus. And another hint we're given there is that we're given the KSP of CuBr. So it's like, okay, if we're given the KSP of copper 1 bromide, then this is probably what I should write a dissociation equation for. So then our KSP is equal to Cu plus times Br minus. And we want to find the max amount of Cu plus. And so that's just equal to KSP over Br minus. And we're given Br minus because its source is this rubidium bromide, which is going to completely dissociate. So KSP is 4.2 times 10 to the negative 8th over Br minus, which is 0.016. And so that is 2.625 times 10 to the negative 6 molar. And that is for copper. And so this is our moles of copper here. Then we can go ahead, or molarity of copper, which we can use for our concentration of copper nitrate. So now we have 2.625 times 10 to the negative 6 moles. I'm going to go ahead and just write moles of copper for now, Cu plus, per 1 liter. And then using that and knowing and with stoichiometry and whatnot, we know that there is 1 mole of copper 1 nitrate for every 1 mole of copper 1, just for completion's sake. And then we also have a volume that we're told, 294 milliliters, which is 0.294 liters. So that cancels out our liters. So now we have moles. And we want milligrams, so we need to go ahead and go from moles to grams. And we know there's 125.55 grams of copper 1 nitrate per 1 mole. So moles cancel. And then lastly, 1,000 milligrams for 1 gram. That gives us 0.0969 milligrams. It's really not a lot, is it? So teeny tiny bit before we start getting a precipitate. All right, number 8, determine the solubility of aluminum hydroxide in a buffer solution at a pH of 7. So pH of 7 means we're nice and neutral. So that means at a pH of 7, our concentration of H3O plus is equal to our concentration of hydroxide. And that means they're both equal to 1 times 10 to the negative 7th power. So hey, that helps. So let's go ahead and write our reaction here. AlOH3 and becoming Al3 plus aqueous plus 3OH minus aqueous. And let's set up an ice table. That doesn't count. We're starting with 0 aluminum. But because we're in a buffer solution, we're in a solution, we have a source of OH minus, and it has a starting concentration of 1 times 10 to the negative 7th power. So the aluminum is gaining some X. That means we're gaining 3X of hydroxide because of that 3 in front of it. So at equilibrium, we have X aluminum and 3X plus 1 times 10 to the negative 7th for hydroxide. All right. So we can go ahead also and just assume that our X is way smaller than 1 times 10 to the negative 7th, because 10 to the negative 7th is already really small. But then look how small this KSP is. So yeah, that's going to be 0. So that makes our lives a lot easier. So now our KSP is equal to the concentration of aluminum 3 plus times OH minus cubed. So that's X times 1 times 10 to the negative 7th cubed, which is X times 1 times 10 to the negative 21st power. And that is equal to KSP, which is 3.7 times 10 to the negative 15. Solving for X, we get that X is equal to 3.7 times 10 to the 6th molar. That is a lot of aluminum hydroxide. So aluminum hydroxide with that pH of 7 has pretty good solubility. Number 9, the KSP for barium sulfate is 1.07 times 10 to the negative 10th. What is the molar solubility of barium sulfate? So this is a nice quick one. So we have BASO4. It's honestly kind of funny that these are like the last questions in the homework. I feel like they should have been the first ones. What do I know, right? I didn't make the website. Ice table. Doesn't count. Starting with 0, gaining X. X, X. So KSP here is equal to barium times sulfate. Nothing is squared or cubed or anything, so that's just X times X, which is X squared. And this is equal to 1.07 times 10 to the negative 10th. Take the square root, and you get that X, which is going to equal concentration of barium, and the concentration of sulfate, which is our molar solubility, is 1.03 times 10 to the negative 5th molar. This would be more of like a multiple choice question. Well, I don't usually give that many math problems on the multiple choice part of an exam. Something that's really quick like this might be something I would do. All right, number 10, the last one for chapter 15. KSP for AJCl is 1.77 times 10 to the negative 10th. What is the molar solubility of it in a solution of 0.45 molar sodium chloride? So this is a common ion effect. You've got an extra source of chloride. But let's first write our reaction for AJCl. It's equilibrium, going to Ag plus Cl minus. And let's make an ice table. This doesn't count. So we're starting with 0 silver, but we can't say we have silver apparently. 0 chloride. We have 0.5 molar to start. Whoops, I keep doing that. Oops. Okay. So this is gaining some X. They're both still gaining X. And then we have 0, 0. Oh, not 0. I've been staring at a computer screen too long, I think. 0.45 plus X. All right, so KSP is equal to Ag plus times Cl minus. And so that is X times 0.45 plus X. And we can go ahead and assume that X is much less than 0.45, so it can go away to 0. So now we get 0.45X is equal to KSP, which is 1.77 times 10 to the negative 10th. So then solving for X, you get X equals 3.93 times 10 to the negative 10th molar for its molar solubility. So it already has a pretty low solubility, but then you add in that little bit of extra salts, and it plummets even more. So that does it for the chapter 15 homework questions. My hand is sore from all that writing. All right, guys, hope you're staying safe. Let me know if you have other questions.